Today, I want to do two things. First of all, from Monday, there was the statement about derivatives and a theorem concerning what happens to differentiability when you take a limit of functions. So I wanted to talk about, finish that proof. And then I want to start talking about series. Series is the next big thing. We'll be spending at least the next 2-3 weeks actually talking about series. So somehow this intro to that is very important. We'll state the most important theorem concerning what we will be using a lot of the time, namely Weierstrass and test. Okay. And then at the end, we will then, because it's so important, we'll hopefully have time at least to state some examples related to that. Okay, so this is from last time we talked about exchanging limits and derivatives or integrals. We stated the theorem that how things, and I'm recalling this because we will use this, that we stated and proved the theorem that if f and are continuous functions, that they converge uniformly to a function f, then the limit function is, well, it's continuous and also Riemann integrable, and that you can exchange the order of integration and limits. So this will play a role in our proof, and that's why it's so important here to mention. So the proof I will now skip. It's also included in the file. We don't now need to discuss it again. It's in the Monday lecture. And we want to prove this theorem that we stated last time. So it looks like a lot of words here, so I will highlight only what's crucial. So you have an open interval, and you have some differentiable functions. Of course, every differentiable function is continuous, so we don't state that they are continuous. We have that the functions converge pointwise to some limit function f, and that the derivatives are continuous. The derivatives exist because it is differentiable, so we can talk about them. And the derivatives converge uniformly to a function g. And then the limit, we conclude that the limit function is differentiable and the derivative of the limit function is equal to g. In other words, the derivative of the limit is the limit of the derivatives. Okay, so the crucial things here, everything else sort of is kind of a technicality. The derivatives we will need to be continuous, and the derivatives need to converge uniformly. These are what you should really focus on in this statement. Okay, how will we prove this? This will actually be based on recalling something, namely the fundamental theorem of calculus from 131a. And there are different ways of stating the fundamental theorem of calculus. So I will state it here in a way that we actually will use it. We'll use it in two different ways. So one way is this way one here. So if you have a function that's differentiable and the derivative is continuous, then the change in the function can be expressed as the integral of its derivative. So this is kind of starting from the function and then expressing it as the integral of its derivative. But the other way is you start from the derivative and you kind of go to the function. And one way of stating this in an equivalent form is that if you have a continuous function, and if you know that this formula is true, so the change in the function is equal to the integral of g, then actually any functions, so this holds for all points b and a in the domain, add in the domain of the function. So here f is always a function on r, and g also should be a function on I. If this is the case, then the limit function, or not limit, the function f is differentiable and its derivative is g. So if you are able to prove this formula is true for the derivative, and if it is true for some other function, then the function is actually differentiable and the function has to be the derivative. This is a little bit different than what you've seen, perhaps, but it's almost equivalent, and I'll leave that as an exercise to think how 2 and 3 are related. This is only using things from 131a. If you have a continuous function and you integrate that function, so for say from 0 to x, then this function is differentiable with derivative equal to g. I mean, basically the idea here is that you put fa on the other side and you define the function as the integral, and you verify that it's the same as f. Any questions on the statement? People state it a little bit differently, so let me know if you're at all confused by any of this. So all of these are sometimes referred to as fundamental theorem of calculus. They're slightly saying different things, but we will use 1 and 2 in this case. Okay, so now let's prove this theorem about derivatives. Well, every proof has a setup. Let fn be differentiable on I. Fn converges pointwise to f. Fn prime are continuous, and Fn prime converge uniformly to a function g. I mean, this is stating the assumptions that we had in the theorem. Again, so now we have such things, and they're defined. And what we want to do next is prove that this limit function f is differentiable. So what we will do is so we pick, actually, to match our theorem, let's pick any two a, b, and I, and then for each n we have by 1 from fundamental theorem of calculus that fn of b minus fn of a is equal to integral from a to b of its derivative fn prime x dx. So this is, we're studying fundamental theorem of calculus here. And the idea next is we take this is now true for all points a, b, and all n. We take the limit on both sides. So let n go to infinity. Now, what happens? Well, the left-hand side here, so for every a, b in the interval, what does the left-hand side converge to? Well, it converges to f of b minus f of a. Why? Because, well, fn of b converges to f of b, and fn of a converges to f of a. So by pointwise convergence, or the left-hand side is by pointwise convergence. Because we're evaluating only for at fixed points. So this is using pointwise. Now this is equal to the limit as n goes to infinity of integral ab fn prime x dx. Now this is a limit of integrals. So by theorem, since, so this is for the right-hand side, by theorem on integrals, since fn prime converge uniformly, and remember we know it by 2 lines, 2 arrows. This is converging uniformly to some function g. Then this right-hand side, you can pass the limit inside the integral. And this is just saying integral from a to b of g of x dx. So what we get is that for all a, b, and I, we get that f of b, the change in the function, is the integral of some function, gx dx. So now by 2 of fundamental theorem of calculus, g is equal to f prime, and f is differentiable. And we're done. So this goes via, the crucial thing here is going via the integrals, and we use ftc twice. First this way to express it as an integral of the derivative, and then we take the limit and then we use it the other way. if you have such a function, then that has to be the derivative. Any questions? Okay, so this is the main way. Now, also before saying one more remark, this kind of way of analyzing derivatives via integrals and using fundamental theorem of calculus, that's actually very important. And the reason for that is that derivatives behave kind of poorly under limits. They are more difficult to analyze, but integrals actually behave very nicely because it's easy to estimate the integral of f minus g if you have two functions by just how far f and g are from each other. So the integrals are easier to estimate actually than the difference in the derivatives, because if you know that fn is close to f, why would the derivatives be close? It's not as easy to analyze, but the integrals are close, and that's why this proof goes via integrals. Okay, now just a small thing, because we'll be talking a lot about this in the rest of the class, so I want to define this thing here. You've seen this probably. If you have a function usually defined on an open interval that is continuously differentiable, it is continuously differentiable, or sometimes called C1, if f is differentiable and its derivative is continuous. So with that terminology here, f is continuously differentiable. So it's an easier way of stating these assumptions than saying differentiable and derivative is continuous. It's just quicker. Okay, that ends that chapter on exchanging limits, exchanging derivatives and limits, and exchanging integrals and limits.